the recording. All right, welcome to our second class. Good to see all of you. It was super fun to see everyone out in the field on Saturday. And we have a break this Saturday, but then we'll be out in the field again the following Saturday. So today we are all about geology. So we are going to dive into geology. So our agenda tonight looks like geology with our guest expert. And then we will take some time. We'll take a break. I promise around 7. I will aim for the break to be closer to 7 this time. If someone wants to volunteer to do a reading after the break, if something occurs to you, send me a message. That would be great. And then we will finish up with geology probably around, I think, 7:30 or so. And we're going to take a short time to kind of join some groups on capstones and just kind of keep that conversation going about the capstones. Oh, thank you, Morgan. Awesome. Morgan's doing our reading. Thank you. And then we'll finish out the evening by talking about what the assignments are for next week. Any questions before we take off, start doing some geology? All right, well, I'll pick up questions also at the end of class about just logistics and geology. I mean, not geology, logistics and homework and stewardship projects and that sort of thing. So I would like to introduce to you somebody who is close to my heart, my dear friend Leslie Tarini Smith, who is a geologist. She is a traveling geologist. She does geology at MPC and at CSUMB and has all kinds of expertise in our local geology. She's also a docent out at Point Lobos, so you might see her on the trail interpreting geology out there. And we are so thankful to have you here with us tonight, Leslie.
Well, thank you. It's a pleasure to be here, and I am happy to share what I know about geology. And please feel free to ask any questions anytime. You can interrupt. I won't see you, but who's ever, Kat or Lisa, if you see a question, just go ahead and interrupt. That's fine.
And I have to say, Kat, I'm working on one screen, so I'm going to need extra help probably catching if there's questions and things. So, but between the two of us, Leslie, we'll try to catch them.
Okay, that's great. And if we don't catch them, when we take the break or when we rejoin or whatever is fine too. Okay, Lisa asked if I would describe and explain California geology, coastal California geology, with the lens of thinking about biodiversity in California, especially in Monterey County, the results of geology and soils on our local region, how that impacts microclimates, also thinking about the sense of time in geology is very different than in our day-to-day lives. We're talking about vast amounts of time. And to also think about the geomorphic impact of the ocean-land interface. So I'm touching on all these topics. So let's start with one of our favorite places, the Big Sur Coast. So looking at the Big Sur Coast, we see it's a region that has frequent thick summer fog, moderate year-round temperatures, and considerable winter rainfall. It's the home of the ancient coastal redwoods, and these redwoods live only along this narrow coastal zone, only 20 to 30 miles wide from central California up to southernmost coastal Oregon. And why are they only in that region? When we think about how this works, we see that the coastal redwoods is the Sequoia sempervirens. A large part of it is because of the geologic forces. The tectonic history has created steep coastal mountains that rise up fast and steep out of the Pacific Ocean. It's also combined with those tectonic forces created these steep mountains. So there's a very strong slope, and that influences the soils that can form on it. Soils don't form as much on steep inclines as they would in a flat valley bottom. I think Lisa probably talked about that in your first week.
Mhm.
It has to do with precipitation. The prevailing winds pick up moisture from the Pacific Ocean, shown there off to the right. They blow towards the land, they hit the mountains. There's orographic uplift where the winds are pushing the air up. As it rises in elevation, it cools and creates rain. So the precipitation is interacting with the rocks and that slope. The rain weathers the native rocks, breaking them down, eroding them, changing the chemistry, forming new minerals. Impacts the type of soils that grow or that form there based on the rocks that those mountains are made of and the weathering and the history they've been through, including the temperature. And all that combines to create a climate that's unique in that area on top of those landforms with those types of rocks. And all of those combine together to create a habitat that is unique for the coastal redwoods. And they only grow in that narrow little region in this one little part from California up to Oregon. One thing we have to think about when we consider how this happens and why it's here is the concept of time. That the geologic forces at play to create these coastal ranges, the amount of time it takes for these soils to develop, for the trees to grow and go through their evolution, is an immense amount of time, far beyond the human time frame and our human lifetime, our human lifespans. John Muir's quote, "When we try to pick out anything by itself, we find it hitched to everything else in the universe." And John Muir, that incredible, influential naturalist, he recognized that the geology was influenced by the plant life and by the atmosphere, by the climate, by the hydrology and the water systems that were there. And all of these different components of nature interact together and influence each other. In earth sciences, we call this the earth system science, that we recognize that geology, the land, does not exist independent of these other spheres. The spheres being air or atmosphere, water or hydrosphere, which includes liquid water, lakes, oceans, frozen glaciers, ice sheets, and life, all forms of life, plants, animals, and including people. And the land includes not just the land we walk on and the rocks and the land surface, but everything inside of it, the molten rock. All of that works together in an earth system that influences each other. If we have a change in one of these systems, it has a cascade effect of changing and influencing the other systems. And the part of our planet that binds all of these spheres together is soil. Soil, it can be thought of as like the thin skin on Earth, and it's the membrane through which all these spheres interact. Here's a picture of the rocks in the bottom here. These are being worn down by weathering, which would be rain and fluids, temperature, baking or freezing, creating soils. And this is the soil horizon right up here. The types of soils are influenced by the chemistry of the rocks that broke down. They're influenced by the amount of precipitation and the temperatures. And that is also influencing the plants that can grow in that particular environment. So just an example of how the soil interacts. The soil interacts with the atmosphere too. Soil has a lot of oxygen and airspace in the pores. That's part of a healthy soil. So we see that the life, the animal life, the plant life, the geology, and the hydrology all interact to create a complex, interrelated Earth system.
Leslie, we talked about soils on Saturday, and I really wanted to show folks a soil profile, but the Carmel River is so high that we couldn't get to the site where we would see a soil profile. But you all, that's what that is. That's a soil profile she's showing there. And so you can see those different horizons that we talked about on Saturday. So you've got a nice example there. You can also look up other pictures of soil profiles, but I love that soils join all the spheres. Thank you, Leslie.
Yeah, this soil is dark. It has a lot of organic matter in it, and the native rock underneath it is not as organic rich, and so it has that color change, which is indication of different soil horizons. So here's an example of interacting spheres that might be more familiar to you. This was Holt Handley on KSBW Local Weather News, reporting the storm rainfall totals we had just in March here. And I've circled two locations, Big Sur and Ben Lomond area. And if you look at those rainfall totals, the Big Sur area and Ben Lomond and the Santa Cruz always seem to get the most amount of rain compared to Monterey, Carmel Valley, and definitely a lot more than Soledad, King City, or Salinas, typically. And what's going on there is the rain, the hydrosphere, the water, is interacting with those coastal mountains, creating the coastal mountains along Big Sur and the coastal mountains up by Ben Lomond. Those are higher mountains, and that causes that orographic uplift, creates the marine moisture that's coming off the Pacific Ocean. That's the hydrosphere, and it creates the rain. So that's why those regions tend to get more rain than we do. And that changes the types of plants that can survive there. It changes the types of soils that will form there. Inland, these are much farther away from the coast, so they just don't have as much moisture coming in, and so you get different habitats and different ecosystems forming. Move something out of the way here so I can see better. There. This was a quote by Arthur Kruckeberg, and he is one of the authors that was quoted in the GeoGems that hopefully someone got a chance to read the chapter that I recommended. The geology is the supreme arbiter and creator of climate in California. And I think that is very well put. Geology and the climate work hand in hand to form landscapes, and these various landscapes create habitats, and these different habitats, they foster biodiversity, which is so rich in our state. So let's dive into why our biodiversity is so rich. And to me, as a geologist, I see this through the geology lens. We have an extremely complex geology in California. Here's a geologic map over here on the left-hand side. All these different colors represent different types of rocks, igneous, metamorphic, sedimentary, and even different subcategories of those types of rocks. Over here on the left is a vegetation map. And you can see that the pattern, the general rough patterns between these are very similar. The geology creates soils in conjunction with the climate, and that influences the life forms and the habitats that form there. So the geologic history, it's a synthesis of the rocks that are present, of plate tectonic history, of climate and change, and again, lots and lots of time. Stratigraphy is the study of rock layers. This is a beautiful picture of the Grand Canyon. And a stratigraphic column is such as shown over here. This is a stratigraphic column of the Grand Canyon when scientists look at these rocks and analyze what types of rocks they are and use different ways of dating to determine their ages. We can stack them in a chronological sequence with the oldest at the bottom and the youngest at the top. And the characteristics of the rocks are exposed in this profile. This is an easy way to visually summarize rocks that are present in a region. And we do the same in Monterey. This is our Southern Monterey Bay stratigraphic column. It doesn't mean that all of these rocks are exposed in every location, but if we take this region and we look at the rocks and analyze them and analyze their dates, we can take a region and put those rocks in a sequence so we can see what the evolution of the geology is over time in this area. Unfortunately, Monterey is not an uninterrupted layer cake of rocks like it is in the Grand Canyon. The California geology is strongly influenced and is a product of shifting tectonic plates. So much of the rock record is missing, like pages in a novel that have been ripped out. We don't know what the rock history was then. It's gone. It's been eroded away. So to understand our California landscape, we got to think about tectonic plate interactions. And just very simply, I'm going to simplify this for what's important to Central California. There are divergent plate boundaries where tectonic plates, and tectonic plates are like patches on a soccer ball, or the plates on a turtle back. Where these plates meet is where the action happens. These plates can pull apart at divergent pull apart boundaries. There are convergent boundaries. One type of convergent boundary where plates push together, we see subduction happening, where one plate gets subducted or pushed under an overriding plate. And of course, most of us are familiar with transform boundaries, where the plates slide past each other in a horizontal way. They're not, nothing's going down or up or down, it's just sliding horizontally past each other. Have they had any of this? Is this sounding kind of familiar, these plate boundaries? Okay, then I don't.
Yeah, this was in your textbook, I think, right?
Good, okay. So when we have subduction, we're looking at this scenario right up here, where plates are being pushed together. One will get stuffed underneath. Typically, it's the oceanic plate, and a continental plate will stay on top. Continental plate is less dense, oceanic plate is more dense. It's the one that always loses. Oh, it works. Took me a while to figure out how to get these little animations to go in here. So watching this little animation, this is subduction. The oceanic plate is colliding, pushing together against the continental plate, and it's forcing the oceanic plate underneath. It's being overridden by this continental plate. What we see happening, the evidence of this, is that as the plate subducts, it heats up, it melts, and the molten rock is less dense than the rock around it. It rises to the surface, and it creates a volcanic mountain chain. And what cools at depth are granitic type rocks that cool beneath the surface. This is analogous to what we see in the Cascade Mountains of Oregon and Washington, with Mount Hood, Mount Rainier, Mount Lassen. All of those are Cascade mountain ranges because of subduction along the coast there.
Leslie, in that animation, there's that kind of yellow lens. Is that showing a material that's eroded out of the mountains and kind of sedimenting in layers there?
Exactly. This is a very simplified diagram. I have another diagram that's a little more detailed, but that's a very important observation that'll be clearer in another diagram.
Okay.
But any kind of mountain, any kind of high spot on Earth is exposed to weathering by rain and temperatures, snow, and all that weathering is wearing down the topography. The high spots of the topography are wearing down, and the sediments that are produced flow through rivers down to low areas and accumulate, like in shallow ocean environments and lakes and valley bottoms. And this little tan stuff is representing the sediments that have eroded off of these volcanic mountains.
I also wanted to let people know that things like the stratigraphic column and those things, those handouts, all of these handouts and the slides will be available to you, but there's a kind of like, you can take your time to look at that layer cake thing. It's in the class website. So all these handouts are in there.
So this was the animation that you looked at if you had a few moments before class, and we'll look at it a few times here. This is how the Western United States looked 40 million years ago. So here's a timeline here. MA is millions of years ago, 40 million years ago with the present at the top. This will rise up as we go through it. As you saw, back then, the North American plate was there, and we're familiar with the Pacific plate, which is the other side of the San Andreas Fault. But 40 million years ago, there was a plate called the Farallon plate that was in between the North American plate and the Pacific plate, which are the two plates we have today. The arrows show the direction the plate is moving. The Farallon plate is heading head-on into the North American plate. These little red triangles indicate it's pointing to the plate that is going to override. It's the one that's going to be on top. The Farallon plate is the one that's going to get stuffed underneath. It's the one that's going to sink underneath the North American plate. The Pacific plate is moving in a northwest direction. It's not going towards the North American plate. And so this red line represents that divergent boundary, the simple diagram I showed originally. These plates are pulling apart and new seafloor is forming here. That's not so important for today. What we really want to watch is what's happening to the Farallon plate and what happens to the North American west coast. So as it starts, the Farallon plate is colliding and cramming into North America. And when that happens, notice here, those teeth disappear. Subduction does not continue. This turns into a transform boundary. As the plate tip, that edge goes underneath, what's left to interact is now really the Pacific plate. And the Pacific plate is not subducting, it's not heading that way, it's moving northwest. So subduction ceases. Now, the Farallon plate, when we go back to the beginning here, it's got this bump out. And so when this part gets subducted, it's now the Pacific plate that turns into the transform boundary and the birth of the San Andreas Fault. And the Farallon plate will be split into two smaller chunks that continue on their original path, colliding with North America. So here you have the collision, subduction ends, the teeth disappear, and we now start having transform. You can see this is the arrow showing it's not a perfect parallel, but it's predominantly a transform slide past. This plate up here becomes the Juan de Fuca plate, and this plate down here is renamed the Cocos plate. They are the little remnants of the original Farallon plate. So some of the questions we thought I asked you to think about was, here's Nevada 40 million years ago. Didn't have as much land mass, was very skinny. And if you watch it go through this cycle here, Farallon plate tip turns into the San Andreas Fault. San Andreas Fault starts sliding northward, but it's not a smooth, slippery slide past. It has a lot of friction. There's a lot of stress in between. And with that stress, part of that North American edge is being dragged along and spread. And so you'll notice that Nevada gets wider and wider. It's being spread and thinned. You see that? I think that's pretty cool. The other thing that's kind of interesting is here's Baja, Mexico, attached to mainland Mexico. All of a sudden, this boundary jumps eastward. Boom, right there. It jumped eastward and filled in this area right here. This is now a divergent boundary, and it forms the Sea of Cortez. That was not there 40 million years ago. It was attached to the mainland. That divergent boundary creates that Sea of Cortez. The Baja is now captured by the Pacific plate, along with much of the central coast of California. Pacific coast grabs it. We'll back up just a little bit here and conveyors it on a conveyor belt up to the northwest, leaving the North American plate completely. So the plate boundary jumps eastward. It becomes a transform boundary with subduction still up here. This is why we see the Cascade Mountain Range. This is subduction with the volcanic mountain chains along here. And there's volcanics down in Mexico too. So it's a
Leslie,
complex thing. Yes.
I was going to say there's a couple of questions. Are you ready to pick them up or you want to finish your
Sure.
thought?
Yeah.
So one of the questions, I'm going to go to the second one first, and that is the Farallon plate, it subducts, and then the Pacific plate is against the North American plate. What happens to the Farallon plate? Does it stop moving is the question.
It doesn't stop moving. What ends up happening with the Farallon plate, I'm going to move this back and forth, it's a little bit easier to see. The Farallon plate, as it disappears, that tip disappears and it becomes the Pacific plate next to the North American plate, it separates into two small plates that continue in that same original direction as the Farallon plate. And we just, we get to choose because we're calling the shots here. We renamed that northern segment of the Farallon plate the Juan de Fuca plate, and the southern end of that remnant Farallon plate is the Cocos plate.
And so those continue to subduct, those two?
Exactly. And you can see
Okay.
the teeth here, and they continue to subduct. And as time goes on, what would you predict will happen to the Juan de Fuca plate? Any ideas?
Anybody? You
Would
can,
it keep getting subducted?
Yes.
yeah.
And as it completely disappears here, that San Andreas fault, if everything else doesn't change, and we know in geology the only thing constant is change, then this will become a transform boundary further north. That San
So
Andreas fault will continue to grow.
so the fact that that Juan de Fuca plate continued to subduct, is that why there's like more recent volcanoes, younger volcanoes up there?
Absolutely. That's the
Okay.
Cascade Mountain Range. That goes
Okay.
back to what this is all about. This is what's happening up of Oregon, Washington, and up into Vancouver.
Okay.
This is the subduction is happening still, and those mountains, this is Mount Lassen, Mount Hood, Mount Rainier, Mount Baker, they're all Mount Shasta, they're all still active volcanoes. Not that they're exploding today, but geologically they're active.
And this relates to Rocco's question. What happens after those plates that subduct under the other plates? What happens to them? Do they just melt and turn into mountains?
Exactly. They just melt. They get incorporated down inside the mantle. And they get recycled. They come back as molten rock and form mountains and come back to recycle again.
May I ask a follow-up question then?
Yeah.
If that happens, and it seems like it's happened down at Baja, when this shift occurs, is that a predictable thing that basically as far as the plate has subducted, it will break away there? Or is is there something else that determines how the plates get rearranged when a subduction event is sort of complete?
Well, that's a really good question, and it's a very exciting part of geology. And if you follow the occurrence of earthquakes through the U.S. Geological Survey, we are finding that the San Andreas Fault at this point is starting to be more active. It's not just one fault; it's a shear zone. It's a broad shear zone of parallel faults, and the easternmost faults are becoming more active. And so the interpretation geologically is this, we've seen this motion of where it jumps from right here and it jumps eastward, which doesn't happen overnight. That the San Andreas Fault is indicating through increased seismic activity to the east that it is working on moving itself further east and capturing more of North American plate to raft up to the north. Good question.
That's related to Rocco's second question. Rocco wants to know if we're going to break off and fall into the ocean. No, I'm just kidding. He didn't ask that. He wants to know, what do geologists predict will happen to California as these plates keep moving?
Well, that's a good question too. And a lot you hear California is going to fall off into the ocean and become an island. But this is not a divergent boundary. The plates are not pulling apart, they're sliding past. In fact, parts of the slide past is actually a slight compression component. It's not pure slide past. It's compression but more predominantly slide past. So to fall off, there would have to be some sort of divergent boundary in between. And as we see what happened with Baja, Baja didn't really fall off into the ocean. It just got separated with a narrow sea called the Sea of Cortez in between. So if it does change and have a more divergent component to the transform, we would expect to have a narrow sea forming there. And actually, if you're in San Francisco and look north of San Francisco, the Tamales Bay has a little bit of that.
Yeah.
It's a narrow bay.
Kathy asks a question related to that, but I'm not sure I understand. She says, so far, the formation of the Sea of Cortez, the Cocos Plate formed a divergent boundary. with the North American plate, which created the new seafloor? I'm not
Yes.
sure I understand.
Yes, that is correct. So here, this to the north is convergent with subduction. Here is the San Andreas Fault. This is a very broad picture, so you can't quite determine that in this view, but at this point, this is a divergent boundary. It's not transformed down by Baja. It's divergent. The Salton Sea east of San Diego is a very, very low region because it's at that boundary of divergent, transforming into the transform boundary of the San Andreas Fault. So in terms of plate tectonics, when we look at all these different types, it is the transform boundary that sutures together convergent boundaries on one side and divergent boundaries on the other, because the planet is not getting bigger and it's not shrinking. So if we have convergent boundaries where land is getting consumed and plates are being consumed, you would think the planet would shrink. It's not. Or divergent, where new crust is being formed, we'd be getting to be a bigger and bigger planet. We're not. The transform sutures those opposite forces and the planet stays the same size, except for the fact that it's cooling, but that's a different topic.
Okay. Ben
Yeah.
has a question as well. Which portions of the land of the central and north coasts are on the Pacific plate versus the North American plate?
That's a really, really good question. Let me show you my a slide coming up that will show that more graphically.
Okay.
So actually, I will ask you that question and I will show you a slide, and I bet you'll be able to answer that, but I will clarify that. Any more questions?
The only other one was the very first one that I kind of skipped. Rachel asked if there are, let's see if I got this right. Did I get it, Rachel? It's something like she asked, are there convergent plates in the ocean? Is there a place in the ocean where there's convergent plates? Is that what you asked, Rachel? I can't see it.
Yeah, so what I was asking is like when in the reading that we had to do for today, there was a portion that says subduction happens because the continental plate is like less dense than the oceanic plate. And they also talked about like two continental plates coming together and then that makes mountains. But they didn't mention anything about like two oceanic plates. And I was just wondering if that was like a thing even for like two oceanic plates to like come together, or like if that actually occurs.
You guys have such great questions. I'm trying to simplify, but you want the nitty gritty, so it's great. So yeah, oceanic crust is very dense and it can't collide. It always subducts, and it has to do with the density difference. It's more dense the deeper down inside of Earth you go, and they're too dense to rise up. They are so dense that they just, one gets subducted under the other. And which oceanic plate gets subducted when you have oceanic plate colliding with oceanic is usually the older one, which is colder. It has had more time to cool. And so it's the one that sinks down. When continents collide, continental crust is much less dense, and it's so fluffy in comparison to the mantle or oceanic crust, it can't go down. And the analogy I use at MPC is if you have a cup of cocoa and you put in a big fat marshmallow, you can push it down, but you let go and it bobs back up to the surface. It's never going to sink down because the marshmallow is less dense than the cocoa. And continental crusts are the same thing, same way. Now, the oceanic crust is dense enough that it can sink. It's like putting in a slab of Hershey's chocolate, the pure chocolate, and down it goes.
Okay, great. Thank you.
So I said to Leslie, you can just cut all that tectonic stuff short, but it's the interesting stuff. So thanks for all of your questions.
Yeah, great questions. Okay, so the subduction, this is another view of subduction. And Lisa, this is the valley here that accumulates the sediments we saw on the previous slide that you talked about. This subduction occurred 40 to 20 million years ago, and that created the Sierra Nevada, the granitic rocks of the Sierra Nevada that were melting at depth at subduction way back in the past, forming that volcanic mountain chain that were the active Sierra Nevadas that have now completely eroded away because we don't have subduction anymore. They're no longer volcanic. But the bowels of those volcanoes that never erupted crystallized at depth to become granitic type rocks. And those are the things that are exposed today, making the Sierra Nevadas. What we also see here is this sediments off the oceanic plate as it's being subducted gets kind of balled up and doesn't get incorporated, just kind of like a pushed together rug. It just kind of gets crammed right here. It's called an accretionary prism. This is a bunch of sea sediments that get kind of metamorphosed by this high temperature and pressure into a metamorphic rock. It doesn't melt. And the San Andreas Fault transported some of the rocks of the Sierra Nevadas north to Monterey. And that's what I want to show next. Well, before that, here's an arc. This is the volcanoes. There's no pretty red to see, but this is the active volcano. This is subduction. We have an oceanic crust, dense, subducting underneath a continental crust, less dense. The melting is not shown here because this is an ancient, no longer active kind of boundary. This would be active volcanoes. There is a basin that forms that we call a forearc basin that accepts all the sediments that are eroding off of these high volcanic mountains. This is that accretionary wedge of the sediments that get rolled up as they scrape off the sea sediments from the subducting plate, and this creates metamorphic rocks. This is exactly the image and the explanation for the model of what we have in California. These are the Sierra Nevadas. That's the magmatic arc or the volcanic mountain chain. Here's the Great Valley, Great Central Valley. That's the forearc basin. And those sediments we call the Great Valley Group. Those deep, deep sediments, great groundwater resource. The coastal ranges here is the accretionary wedge, that scraped up ocean sediments that got metamorphosed and created the Franciscan Formation. Maybe you're familiar with the Franciscan Formation as one of our local common rocks. And this is what we see. This is the result of an ancient subduction zone that is no longer active, but the geologic record is preserved in the rocks. The granitic Sierra Nevadas, the Great Valley sequence of sediments, and coastal ranges that are filled with metamorphic rocks. So
locally, sorry, Leslie, locally we see cool things like serpentine or marble because they're part of that Franciscan kind of jumbled up stuff, metamorphic stuff.
Exactly. If you go down to San Luis Obispo, there's a lot of serpentine and Figueroa Mountain in the San Ynez. Pico Blanco in Big Sur, where the Boy Scout camp is. Pico Blanco is marble. It's metamorphosed limestone, which is sediments that accumulate on the ocean floor. Those are all evidence of being an accretionary wedge. They're both metamorphic rocks. So the main point here is why go through all this tectonic history? Because it creates modern topographies, and those modern topographies are very different and create habitats, and all of these different habitats foster biodiversity. That's the point. This is why we care, besides the fact geology is great. So here's that same diagram. This is a picture showing some of the big broad view of the rocks. These are the Sierra Nevada. Batholith just means these are metamorphosed. These are the igneous rocks of the Sierra Nevada, the granitic rocks. Batholith is a fancy name for a magma chamber that's crystallized. These are now exposed at the surface of the earth because of long, long erosion. Here's the Great Valley sequence. And here's the coastal ranges. These are Mesozoic and granitic rocks, the red ones. And we see that they're here too. Well, wait a minute. There's only one magmatic arc. I understand that the Sierra Nevadas are here, but how did we get granitic rock over here? That doesn't make sense until we dig deeper. But just to back up for a minute, one thing I love about that animation that you looked at before class, the stretching of Nevada, that created the Basin and Range Province in Nevada, which is characterized by repeated horsts and grabens. Horsts are uplifted mountain blocks, and grabens, you can see here, these are faults that show the graben is a down drop block. If you stretch enough, crustal material will crack and fracture and break, and where it breaks, the low valleys will form. And so if you go over the Basin and Range, you go over a mountain range, down into the valley, over a mountain range, down in the valley. You're actually horsed and grabening your way across Nevada. Another example of the rocks record the events of the tectonics, and it creates unique habitats with unique animals and critters.
Leslie, we had another kind of trivia question here.
Okay.
There on that last picture, there are still some hot springs on the east side of the Sierra. How do we still have hot springs on the east side of the Sierra?
So, in subsurface, there are local places where there's high heat flow deep underneath the surface of the earth. Doesn't mean it's a volcano. Doesn't mean we have subduction, but it's uneven in the heat underneath the surface of the earth from the magma. And if you get places where it has fractured rocks that it can come close to the surface, that heats the groundwater, and then we get those lovely hot springs. There's beautiful hot springs in Big Sur too. Okay, so this is another great animation. This is the one that shows it a little bit more close in for us. This is 20 million years ago. So halfway through the time sequence of that first one. You see the triangles, that tells us subduction is to the south. Here's the San Andreas Fault, and here's more subduction with the Juan de Fuca plate up here. Juan de Fuca is still colliding with North America. The Pacific plate is basically moving roughly parallel to the North American plate. This SD, this is 20 million years ago. This is where modern day San Diego started. 20 million years ago, SB is Santa Barbara, and SF is San Francisco. And as we run this, we'll see how this evolves in this close-up view and what happens to those towns and those geographic markers. You can see there's a pop in eastward of the San Andreas Fault. And we've got Baja, Mexico, and San Francisco moving north. You saw that rotation. That's the transverse range by Santa Barbara. A chunk of land, a chunk of crustal material was captured in this subduction and this transformed transition and twisted it and brought those mountains up. This is along the Garlock Fault. So San Diego's moving north. Here's Los Angeles. Here's Santa Barbara today. Here we are. We're right here. So that previous question I deferred. Here's the little puka for Monterey Bay. Which plate are we on? The plate boundary is the red line. So we're on the Pacific plate. And if you think about where are our active local earthquakes, it's like Hollister, east of here. The Calaveras Fault is that way. So we are actually on the Pacific plate. I know we're on the North American continent, but we're on the Pacific plate, and we are slowly moving to the north. So the West Coast tectonics shifted from subduction to transform, and the birth of the San Andreas Fault was approximately 23 million years ago. And the way we can date this is by looking at the story of the rocks, looking at the rock evidence. And if we look at the California geology map, this is the Sierra Nevada granitic rocks. Here's the Garlock Fault and that twisted block by Santa Barbara also contributed to the Channel Islands here. There was more volcanism in the past further to the south, but look right here where we are. This is Monterey Bay. There's some red right here. This red is the same type of rock and the same ages as the Sierra Nevadas and further south. And that is because those rocks were snagged by the San Andreas Fault, by that transform boundary, have been ripped off the southern tip of the Sierra Nevadas and transported north. Does that make sense? Mark is looking like he's scowling. He's either got a question or he doesn't believe it.
It makes sense, but it's crazy.
It is crazy. I agree. It's very crazy. So how do we know those are the same? We look at the geochemistry of these rocks and the Sierra Nevadas, and we find it's the same. And there's lots of other pieces of evidence as well. Point Lobos exists because of its rocks. Now, I'm a docent, so I got to throw in some Point Lobos here, but it's our local geology too. The granitic rock was scraped off that southern Sierra Nevada mountains, and they were transported north along the San Andreas Fault, like that previous animation. And this faulting, not only the plate boundary, but the immense faulting that occurs all along this shear zone that we call the San Andreas Fault, along the transform boundary, creates really unique landscapes and biomes of Point Lobos State Natural Reserve. These coves and all of these fractured granitic rocks, these are all granitic rocks, the same signature rocks as the Sierra Nevadas, are here because of that transform boundary. Originally, even further back, by a subduction zone. And it makes a very unique ocean-land interface. For example, the Monterey cypress is only found in a few select places. It grows on these granitic rocks in this climate and this location, and the only native habitat is here in Point Lobos and another place on Pebble Beach. Now, Monterey cypress will grow in other places, many places around the world, but these are considered the only two native stands of Monterey cypress. Uniquely situated to grow in this region, and this region is predominantly influenced by its geologic history. Another thing about Point Lobos is we see the giant kelp that grow right off the shores there. You don't see those off of Marina. You just don't see those big kelp beds. The giant kelp in our bays give us clues on what's below the surface, because kelp thrives where it can anchor onto a rocky seafloor. It needs rocky seafloor to grow and thrive. And the seafloor below, near Point Lobos, is the same rocks as we see on land. It's just been covered up by the seawater. And it's granitic. It's carried north for 23 million years. And that kelp forest is a key habitat for the southern sea otter, up and down the Big Sur coast and along Point Lobos. So this geology influences the animals that can survive here and the plants that survive here. Pinnacles is another key piece of information that help us understand when the San Andreas Fault started its offset. Here is a map of California. Here's the Pinnacles National Monument, and here's a formation called the Nenach. And the Nenach is much further south, kind of near Mojave. It's east of Mojave. It was an active volcano when California was a subduction zone and had active volcanism. When the San Andreas Fault started, it just happened to replace that subduction zone, but the San Andreas Fault, that boundary, split the Pinnacles volcanic formation in half. And one half, the Pinnacles, lucky for us, is captured by the Pacific Plate. And the Nenach, the other half of that original active volcano, is over down by Mojave. It's on the North American plate. It was split by the San Andreas Fault. So when we look at the geochemistry of these rocks, of these igneous rocks, and compare them with the Nenach, we find that they're exactly the same. There's multiple minerals that have that same geochemical signature, and they are of the same date. And they've been dated about 23 million years ago. And the offset between these is 195 miles. And we can do a quick calculation. The average rate of motion along the San Andreas Fault for the last 23 million years is about 3 centimeters a year, about the rate that your fingernail grows. Okay. Should I keep going? I'm going to start a kind of a new topic, but I can keep
I-
going.
We could, or we could take our break now. So you tell me, because somebody asked a question about the canyon, the Monterey Canyon and stuff, and I said, hold that question because I think it's coming.
It's a coming.
It's a coming. All right. One
Yeah.
other quick question is somebody asked, Ben asked, is Point Reyes the only portion of the coast north of San Francisco that's on the Pacific plate?
No, it's not the only portion, but it does have similar rocks to what we find at Point Lobos.
Hmm.
So I'm not going to go over Point Lobos rocks, but aren't there a couple of docents here in this class?
Point Lobos
Are there?
docents? We usually do, but I don't think we do this year. We almost always
Oh.
do, but I don't think we do this year.
Okay. If you've been to Point Lobos and you see the big conglomerate down there, those rocks are the same age as some conglomerates that are conglomerate sedimentary rocks that are found up by Point Reyes. And they are part of that shear zone. And so they've been shaved off and they've transported up north as well.
And yet, Yasmin and Dimitri ask, how do you date rocks?
Well, I am not a geochemist, but they look at minerals, they look at the isotopes, the unstable isotopes inside of minerals, and they do isotopic analysis, calculate how old they are, and they look for the signatures. For all rocks, they look at several different minerals in a rock, not just one, so that they have multiple lines of evidence that come up with the ages of the rocks. But it's really looking at radioactive decay of unstable isotopes and minerals.
Sounds good. So Leslie, do you think now would be a good time for us to take a 5-minute break?
We can do that now, or I can do a little bit more. Your choice.
Either way. I don't
Okay,
know how much.
let me dive into sea level, then we come back,
Okay.
we'll talk about the topography and the impacts and what we see specifically around here. That might be a good
Okay.
place to break.
Perfect. Sounds good.
So we've talked a lot about the tectonics. Now let's add sea level. This is another big monkey wrench in how things are interpreted. Sea level changes over time, and it causes a dramatic change to landscape and habitats. This is a map of the East Coast. You might recognize Florida as being a good landmark here. During the Pliocene, 3 million years ago, it was a very warm climate. We are experiencing warming climates now. We know, what does that mean? It means that ice sheets are melting. It means we don't get as much snow, that glaciers are retreating. All of that frozen water is draining to the ocean and filling up the oceans. So during that last warm period in the Pliocene 3 million years ago, the coastline was the boundary between the light green and the dark green. That's where the beach was. Florida was underwater. Now, 120 meters deeper, this was the coastline here between the light blue and the dark blue. And this was the boundary at the end of the last ice age about 11,000 years ago. During ice ages, when the temperature of the planet cools, more rain falls on land. It freezes as snow and it accumulates as glaciers, builds ice sheets. And so less water is melting to go back to the oceans. And in a global sense, we get a lowering of sea level because of those climatic changes. Back during, at the last ice age, at the end of the last ice age, where sea level was much lower, it was way out here. So we see that shoreline, and thinking about the habitats that happen at shorelines, this is a dramatic shift based on sea level changes. And sea level, this is a complicated graph, but the only message to get here is that sea level changes a lot all through Earth's history. The bottom axis here is millions of years before present. The present is over here with the 0. We're going back in time as we go to the left. This axis is relative sea level in meters. And because we drew this map and we're living here today, this is 0 sea level today, and here's time today. If we go back in time, it was lower and higher, lower, higher. It has changed dramatically over geologic history. And that changes the shorelines, and that changes the rocks. So what does changing sea level do here for us as an example? is that when we have sea level rise, it creates drowned river valleys along the coast. River valleys form when the land that's above sea level is eroded by rivers and rain falling in the mountains, and it drains to the ocean. And that river and sediment creates river valleys. It grinds down through the sediments and through the rock and creates a valley. When sea level rises, those valleys are flooded. They're a low spot and they flood in. This is a picture of showing many valleys that have been flooded by a rising sea level. Here's Lake Estero in Monterey. It's technically a flooded river valley as well. When sea level was lower, this was a valley with a river flowing to an ocean that was much further out to sea than shoreline was much further out than it is today. And this picture, I couldn't get one with the Pacific Ocean, but if you know El Estero, and this is Shoreline Park right here, the Pacific Ocean is 1 block away. It's just the other side of this little grassy area. So this is a flooded river valley. If you go up this arm, you're going up through Iris Canyon next to MPC. It's also a managed lake so that it doesn't ever get muddy and stinky and no water. We manage the water volume, but it is a natural flooded river valley, and it creates a unique habitat, brackish coastal habitat, creates a new environment for different unique animals, and increases biodiversity just in our neighborhood. Okay, this might be a good place to stop. When we come back, we'll talk about what does sea level rise do in conjunction with tectonics to create some other shoreline features.
Sounds exciting. So synchronize our watches. It is 7:02. So I will see you back here at 7:07. Take a break, and then Morgan has a reading for us. Reading. And take it away, Morgan.
Okay, so this is from a book by Adam Nicholson called I hate that you can't see that. Life Between the Tides. There we go. It's a very good, he's a very good author. You should check out his other books. But so just some context, he just finished quoting a I don't know if she's a naturalist or scientist, Iris Murdoch. So he like quotes her. So at one point towards the end of this part that I'm going to read, he says she, and that's the she that he's referring to. So he says, it is not that nature itself is valuable. There is no more value in it than there is in us, but the opportunity it provides to amend our consciousness, to remove the unending claims of the self, to deny the primacy of the self as anything more than a ripple in the general flux of the world, is a moment of education in what she called the intolerably chancy and incomplete nature of being.
Thank you. That's awesome. And if you would, on our contact sheet where it says potluck reading, if you want to, well, I guess actually Kat's just put the link in here. I was going to say we can put a link in there. That's
Yeah, I can
awesome.
add that. I can add that to the sheet. And just so you know, folks, this is directly to the publisher, so you can decide where you want to purchase it if you want to purchase it.
Awesome. Thank you, Morgan, for sharing that. And others, please sign up for weeks in the future. I'd love to hear what you all find moving and interesting. All right. Do you want to jump right back in, Leslie? Or do we need to
Sure.
take care of any other business? Anybody need anything answered?
I love your potluck reading. That is a wonderful, wonderful activity. That's great.
Well, it should be brownies, but you know, on Zoom it's tough.
Yeah, that's a good one though, even with brownies or without brownies.
Yeah. All right, take it away. We're ready to roll. I get my notes.
Okay, so we finished up with sea level is rising and falling repeatedly over its history. We see drowned river valleys along the coast as a consequence of current sea level rise. But sea level rise and tectonics interact in other ways that dramatically impact the coastal region. And so what we have here, and I'll show this a couple of times, we know that sea level over time rises.
I don't think we're seeing your screen though.
Oh, that's a problem.
Yeah.
Well, I like this little video. Let me get this to stop. There we go. You see it now?
Yes, we got it.
Okay. So sea level rises over time on the shoreline, and we know that sea level over time falls, and it cycles back and forth. And if we stop and look at a condition where sea level is stationary for a long periods of time, it can create a notch at that current sea level and create what we call a wave cut platform. It's a platform, a flat surface created by the waves. Now notice we're starting to add an arrow, so we're having tectonic uplift in conjunction with sea level rising and falling. Changes, falls, and then it comes back up, and the whole time the land is being pushed up. It's the sea levels returning and creating a notch. And so we get these terraces on the shoreline. And these are beautiful places to build houses with lovely ocean views. But we know that the sea level will continue to erode any kind of coastal bluffs. And that's where we start losing houses into the ocean. And there's lots of places with examples like that, like Pacifica up by San Francisco, parts of Los Angeles along the coast there. We have all sorts of erosion happening along Hope Ranch in Santa Barbara. So we have sea level, it creates these wave cut platforms when it lingers at a certain spot. And then it changes because of global conditions and creates a new wave cut platform at its new sea level. Add this tectonic uplift component, and it's adding two forces at once. The tectonic uplift will take that wave cut platform and lift it up above sea level, even if sea level's rising and falling. and we get these stair step of marine terraces. So this is a picture of a wave cut platform and marine terrace. This is Andrew Malera State Park. Right here, you see this rocky surface. The waves have power to erode to the height of the wave below the surface of the water, and it will erode any of that rock material through the motion of these waves, the erosional force of the waves, and create a flat rocky surface at sea level. And where it intersects with the coastline, it will erode that coastline. Here is a flat surface, but it's up above sea level. This was originally formed by a wave cut platform in the past when sea level was higher. But along this part of our coastline, we have a lot of uplift, and it's taken a wave cut platform from the past, lifted it up above sea level, and creating a new wave cut platform at this new level for sea. Another way of looking at this in a still, actually, before I go, does that make sense? Are people following that animation? Is that clear?
Did you
I
have a
followed
question?
I
Yeah.
did. Yeah, I followed the animation. I was just wondering if you could talk a little bit more about what causes tectonic uplift, like why it's going up.
Yes, so we know that the transform boundary along the San Andreas Fault is mostly transform, but it's not pure transform. It's not a smooth slipping surface. In some places, it slightly pulls apart, like the Salton Sea down in San Diego. In other parts, like along the Big Sur coast, there's a strong compressional component. And when you get compression, you get continental crust is going to push up. It's not going to sink down into the oceanic crust. So it has both those things going on. So this is a diagram kind of showing the same thing, but it's in stills. It's sometimes easier to see. Here is a diagram showing what sea level is doing. We know it rises and falls and rises and falls. This little gray tells you this is in this diagram, sea level's higher. It's kind of at its high zone. So here we have a sea cliff with this notch being formed at the current sea level. This abrasion platform is another word for wave cut platform. It means that flat surface created by sea level. If uplift continues and sea level drops, see over here, it's showing that sea level is lowered. Here, sea level is lowered. These arrows are showing what sea level is doing. That is now an abandoned wave cut platform. It's no longer being eroded. And this sea level will create a new sea level at a new location. And this uplift pushes a previous wave cut platform up above sea level. So in the third place here, we have another high stand of sea level. It's come up, it's now eroding a new notch, but that uplifted marine terrace, which formed up here, is now well above sea level, and we get the staircase. We have these all over our region. If we stand at Monastery Beach and look north towards the river, Carmel River mouth, the Carmel River Beach, there's that neighborhood right to the south of Monastery Beach. It's called the Ribera neighborhood, or I forget what the name of that neighborhood, but it has Ribera is the main street. This red line shows 2 marine terraces. It even has the nice little houses, beautiful houses built on them. So this is one marine terrace, and higher up, this is an older marine terrace created by those same forces. And we also see these rocky rocks all along the cliffs here. These are the same granite as at Point Lobos, just across the bay. Here are some more pictures. This is that same monastery view. And up by north of Santa Cruz at Davenport, you can see many marine terraces. Here's the current sea level today. Here's the modern sea cliff. Here's the first marine terrace. This flat surface is a second marine terrace, 70 to 80 meters higher than sea level. And a third one is way over here on these mountains. And those are 150 to 160 meters higher than modern sea level. This is the view of the Bixby Bridge right here. This is the Big Sur coast. See these flat surfaces? Those are uplifted wave cut platforms. They're marine terraces. If you ever go down to the Big Sur Lighthouse, that big, broad, flat area where the happiest cows on the planet sit there and graze on those luscious grasses overlooking the Big Sur Pacific Ocean, that's a marine terrace, uplifted wave cut platform. It's because of the tectonics. The tectonics has a compression there and it's uplifted over time as sea level has risen and fallen and made notches and lifted these wave cut platforms above sea level. This is a view of Garrapatta Beach with a bunch of my students in the past. There's a bunch of flat surfaces here that you walk out, you park by Highway 1 and you go down along a flat surface above the beach. That's a wave cut platform. I'm sorry, that's a marine terrace. It's an uplifted wave cut platform. Those are two drawings showing where those wave cut platforms are. Marine terraces. Sorry, I keep saying the wrong word. It's a marine terrace. So marine terraces are interesting. They create new ecosystems. This was a diagram pulled from that USGS reading that was part of the optional reading. And these terraces, this mark right here, these are considered nutrient poor soils often with hardpan. That's the top of these terraces. They are young soil horizons. They don't have a lot of organic matter. There's a lot of minerals in there because these are basically newly uplifted with sediments, sea sediments and seawater saturated sediments in the past. And so these are very nutrient poor and they get these pygmy forests. These are not tall, abundant trees that grow on these terraces, on these uplifted terraces. It takes more soil formation and more variety to grow different types of forests. I find I live at the mouth of Carmel Valley and I'm on a marine terrace and I have old California oaks in my front, Quercus agrifolia, and they're just shrubby little things. Even though they are living in a garden, they just don't have a lot of soil. It's that poor terrace material and they're just never going to be big trees. They're just going to be kind of like small, pretty oak trees.
And this example in Mendocino is like the classic like marine terrace example, but we see it also with the plants around here. And when we hike in Point Lobos in the Del Monte Forest with Nikki Nedeff in a couple of weeks, she will show us evidence of this. So if you haven't looked at this supplemental reading, it is definitely worth checking out.
This USGS article is very good. I recommend it. It touches on a lot of the topics. It touches on the soils and the ecosystems and the geology. It's great. It's really a nice article. So this was your question, I think, Kathy. The Big Sur coastline, it exhibits rapid tectonic uplift. It has, and the evidence of that is that these are steep coastal cliffs. There's only little pocket beaches. They're not well-defined beaches. There's no terraces. This part of the Big Sur has rapid tectonic uplift because of the San Andreas Fault at that point has more of a compression component. And that's creating different habitats just a few dozen miles down the coast. And another example of that geomorphic impact of that ocean-land interface and how that affects habitats and biodiversity. So let's go a little bit further north. We just looked at the Big Sur rocky coast, and this is the Marina coastline, just approximately 20 miles to the north. Not a single rock to be seen in sight. Big sand dunes, big, broad, sandy beaches. How can we have such different geology so close to each other geographically? Why are they so different when you compare the Marina sandy shore that's only 5 miles north of Pacific Grove? And Pacific Grove has a very rocky shore. I'll give you a clue. These are the similar granitic type rocks that you find at the Sierra Nevadas and that you find at Point Lobos. So what happened to the granitic rocks here? Why are they not in Marina? And that we can answer by looking at a Southern Monterey Bay geologic map. All the different colors show different types of rocks. The black lines represent faults, and faults have shifted the land surfaces. And so the old 80-million-year-old granite that formed in the Sierra Nevadas and were rafted north are the pinks and this tan color here along the edge of PG, Pacific Grove. But up by Marina, we have different soils and we don't get the rocks. The faults have changed the what's been exposed at the surface. And this has been uplifted and everything above it has been eroded away, where here this has not been uplifted as much and it now has the modern sediments covering it up. If we drilled down underneath here, we eventually would find those granitic rocks, but they've been offset and the faults continue on under the ocean here. We can just map them more effectively on land here. They're assumed to continue underneath. So where did all this sand come from? We know it didn't come from the granitic rocks eroding. And here we get to look again at sea level changes. And here is that Monterey. Here's the Monterey submarine canyon right off of Moss Landing. This is a bathymetric map. It shows the lines show the contours of the depths below sea level. This green circle shows Marina and the seaside area where we were just looking at those sandy beaches. Here is a diagram showing what you're seeing in map view here in profile view. Here's the land, and right offshore is a broad flat area called the continental shelf. And farther offshore, you get to a steep area where all these lines are close together. That's the continental rise or slope. And that's where we get the submarine canyons, like the Monterey Canyon, that are carved into there, generally during lower stands of sea level and out to the deep ocean in the abyssal plains. So in past, this continental shelf was exposed when sea level was lower. This is an animation showing a model of sea level rise in the Monterey Bay over the last 18,000 years. And 18,000 years ago, it was an ice age. So sea level was much, much lower. And all of this land surface was exposed above the sea. It was dry land. Before I start this, so here is Moss Landing. Here is, I think it had the names here, yeah. Moss Landing, here's the Salinas Valley in the back. Here's Carmel Valley. Here's Seaside and Marina. This is the Monterey Canyon, the submarine Monterey Canyon. So 18,000 years ago, that was sea level. This is the coastline. And over time, going by millions of years, it encroaches on the land. It causes the flooded river valleys. Until we get to the modern coastline today. So in the past, if all of this was exposed fine-grained sediments and sands, and we have prevailing winds that come off the Pacific Ocean blowing towards land, those winds picked up all of these sands and deposited them in the seaside area. And so what we see in Seaside is we've got a lot of well-developed sand dunes and sandy cliffs, and even further inland, we have stabilized sand dunes. And I don't know if you have a speaker that's going to go over those types of things, Lisa, but these are used to be active sand dunes that are now stabilized by vegetation. And
if we can get him, David Steyer is gonna hike with us in Fort Ord. And so he can talk about these stabilized sand dunes, and they give rise to very specific kinds of plant communities.
So that's where the sand came from for these areas. And this area has a different tectonic history, accentuated by the faults in our region, so that we have different types of habitats, different types of soils, different types of environments very close together. So Central coastal California landscapes, they're a product of a complex tectonic history with climatic change that induces sea level changes, that induce all sorts of change in the coastal geomorphology. Here is the Monterey Bay area with Point Lobos, and some more. The hot pink here is the granitic type of rocks that are analogous, and the same rocks that came from the Sierra Nevadas. In fact, it's called, well, these are ripped off the southern edge of the Sierra Nevadas and rafted north along the San Andreas Fault. These black lines represent faults, and you can see it's not just a single fault, it's a shear zone. And each of these sections between the faults can move north at different rates, depending on which fault takes on the motion when we have seismic activity, when we have earthquakes. They don't move all at the same rate. And that's how we can get Point Reyes much further north than Point Lobos. So to summarize, the geologic history of coastal California is really a synthesis of these Earth system interactions of the land, and the atmosphere, and the hydrosphere, and the biosphere. It's a product of the rocks that are present, of massive tectonic shifts, of climate change, including sea level rising and falling, cooling times, warming periods, the impact on sea level rising and falling and interacting with the coast, and changes over vast geologic time. Those granitic rocks of the Sierra Nevadas, those crystallized and formed 80 million years ago. San Andreas Fault has been slowly shoving its land further north 23 million years or more. And all of those things combine to give us the features that we see, like the steep coastal mountains of Big Sur, the rocky shorelines of Pacific Grove and Point Lobos, the sandy shorelines of Seaside and Marina, the marine terraces up and down the coast, sand dunes, drowned river valleys, and a varieties of rocks and soils, and of course faults that kind of shake things up every now and then and cause more changes. And all of these combine in an Earth system science view to create a wide variety of habitats and the high biodiversity we see in Monterey County. So California's complex geologic history and climate, to reiterate, work hand in hand to make unique landscapes, create varied habitats, and foster biodiversity. And I think that's the last. This is Point Lobos. So now I'm ready for any more questions.
I bet there's a few. Anybody want to throw out some questions? Leslie,
I have
can
one.
you? Oh, go for it. Who's that?
It's me, Chris. Leslie, you talked earlier about oceanic plates converging, and one of them would be older and one would be younger, so that would determine which one's subducted. Can you give an example of where those type of oceanic plates exist that converge? Because I've heard about oceanic plates that diverge that form the mid-oceanic ridge.
Right.
But I hadn't heard about the converging type, so I'm curious about that.
Yes. The Japan Islands
Oh, okay.
are a place where the Pacific Ocean is it's not against the Eurasian plate, but there's a smaller oceanic plate between the Pacific plate and the Eurasian plate, and it's subducting. And so you get the subduction and you get volcanic mountains. And we know Japan, Mount Fuji, a world famous volcanic mountain that came from the oceanic subduction.
Great. That's a great example. Thank you.
You're welcome.
Leslie, one of the things that I wanted to ask is, well, two things. All right, first question. So you're showing a picture of Toro Peak, I think, that we're looking there. So this is the edge of the continent, and I know there's uplift, but why do we see like Why doesn't the land just uniformly rise up? Why do we see like mountains like Toro Peak and Fremont Peak and things?
It doesn't uniformly rise up. When we have tectonic boundaries, there's different rocks with different rock strengths. And so some are going to erode faster, some are going to be more resistant. The boundary isn't a straight line. That's another component. And so there's points that have more pressure and places that are of less horizontal pressures that would change the forces. Why we have Toro Peak, I'll have to think about that. I mean, what I described is the coastal geology, but there's been in the past, let's see, Toro Peak does have a lot of marble. It does have a lot of marble. So it's a remnant of that accretionary wedge time when it was subduction.
And so it just eroded slower than what's around it.
Right.
Okay.
Yeah.
Okay.
And the whole coastline is, as that other question or this other map, it's just splintered. And this is just, the peninsula area. The whole California is just a splintering of shear zone. And so things get shifted. It's not going to be a continuous accretionary wedge all up and down the coast because it's been so fractured by that shear zone of the San Andreas Fault, the Pacific Plate rubbing against the North American Plate.
Got it. Other questions for Leslie, the expert, while we've got her?
I have a weirdly specific question about a rock or rocks that I've seen. I'll turn my camera on. So how come when you're driving like through the Central Valley, like you're going to Yosemite and you're like you're getting to like the foothills kind of, but it's still like farmland and like grass and cows and there are these little piles of rock that just seem to like come up out of the ground out of nowhere. I think they're granite, but like I feel like I'm sort of connecting the dots about why it happens, but I need some help.
I've seen those too. Yeah, they're really interesting because it's just a very smooth, eroded landscape, and all of a sudden you get this big rocky knob
Yeah,
coming
yeah.
out. So I'm not going to suggest this applies to every single one of them, but one thing that is kind of interesting, and we see them on the east side of Pinnacles National Monument, kind of the same sort of look of a grassy grazing area with just this anomalous rocky mass coming out of it. And along the San Andreas Fault, it will, when it's moving, it'll snag chunks of crustal material and bring it. And I think they're called, and it just becomes a relocated hard rocky blob, for not a very technical term. And I think they're called knockers. So they're just rocky things, rocky substances that have been captured and rolled along like crumbs along the San Andreas Fault. Now I know I've seen them going up to like Lake Shaver and Huntington Lake up out of Fresno. I've seen what you're describing. I'm not sure if those particular ones are the knockers either, but you can, as you go just south of the Pinnacles National Park, it's not a monument anymore, it's a park.
Yeah.
Just south on the east side, you will see the knockers that are similar to what you're describing.
Yeah, now that you mention it, I remember seeing them there as well and being like, oh, those are the same. Yeah. Cool, thank you.
You're welcome. Yeah, those
Leslie,
are
can
kind
I
of
ask
fun.
you? Oh,
Go ahead, Mary.
can I ask you about just further north? So, when you get up past where the Pacific Plate kind of comes in north of San Francisco and Tomales Bay. What's going on up there with the fault line being, like, I think it goes further off into the shore, but it's still like a rocky coast that goes down. And Mendocino, the cliffs of Mendocino are particularly prominent where it's like they're very steep and sudden. Is it just the erosion of the ocean, or are there other sort of tectonic things that are afoot?
Well, you're right, north of San Francisco. Let me see if I can pull up a map quickly here of that region. So the rocks all form from different eras, from different ages, from different lithologies. Some are more resistant, some are softer. They've been pushed around by this faulting. I'm trying to find. I'm not sure if I'm going to be able to find this very effectively. But as you get further north, the San Andreas main boundary does dive off into the ocean. Tomales Bay is the northernmost part where it's still on land for a ways, and that's why Tomales Bay is like a narrow sea. And then it becomes a transform boundary that connects to the Juan de Fuca Plate, which is still a divergent boundary further to the north. And that's where you end up getting that triple junction. But the rocks of Point Reyes, I'm not as familiar with, so I don't want to misstate. I don't think I'm going to find the image I want very quickly here.
We can look up a USGS map, and USGS is great for maps. You can find
True.
some.
I can check it out. Yeah.
Yeah. And then if we find one, we can share it, with everyone. But I think it would be cool to look at Point Reyes and, just I'm curious too about the rocks up there and how they compare to what's going on down
Well,
here.
and if there's sort of the same sort of fracture faults that Leslie, that you kind of had on the Monterey map, where there's this kind of, does that happen all along the California coast, or is it unique to certain regions?
Yeah, Point Reyes is still that shear zone where you end up with slivers that are moving north at different rates, and so you're getting different rock types. In some coastal areas, you get what's called exotic terrains, where during that subduction zone time, it has land masses that were crammed into the North American coast and sutured on. They didn't subduct. They were more continental in character. And so you end up with these different types of rocks that are very dissimilar to anything around it because it came rafting across on oceanic crust and came from a different environment completely. I don't know how much of that occurs up in Point Reyes, but it can create a lot of different geology that doesn't seem to fit with the regional picture, and they're called exotic terrains. And I know there's some further north.
Cool. Other questions? Let's pull up all the questions we got. I love having the geology talk first. Leslie, thank you so much because of the way you brought together all of the spheres and the way in which geology sets the tone for so many of the other things that we're going to study. So basically, you just had an overview of what we're going to study over the whole course, and starting next week with water and, and then we learn about plants and the animals. And so they just all relate. So geology is a great place to start.
It is a foundational viewpoint because from that is where the soils come and the shape of the land, the geomorphology, whether you have mountains or cliffs or valleys, all of those lay the foundation for everything else to form on top of that. So it's really fascinating, and I really enjoyed sharing what I know with everyone.
Thank you.
And I hope to be taking this class with Lisa sometime in the future myself. I'm
You're
sure
welcome.
I'd learn a lot.
Teach it. Many thank yous to you, and there's many thank yous in the chat from the class. Thank you so much for being here.
You're so welcome.
So I will release Leslie to go get her dinner, I'm sure. And the rest of you, we're going to take a minute and talk about our stewardship projects. Many thank yous to you, Leslie, from
Thank
all
you.
the
And
class.
thank you for inviting me, and good luck with the rest of your class.
Thank you. Take care. All right, crew. So next week, I'll talk about next week when I wrap up. Let's talk about stewardship projects. So shifting gears. What I need to do is I need to get a sense of what projects are emerging, because what I'd like to do is to start to have people kind of organizing into some groups, and then we're gonna start to create the documents that you need to submit. So the documents are found in the class website. If you go down to the very bottom, stewardship project, there's one that's a PDF and one that's a Word document so that you can fill it in. And it asks you to fill in one of those per group. So some of the groups that I was talking with on Saturday were, really big. So I'm thinking that, you all might be organizing yourselves into like a couple of smaller groups or something. Can people help me
Lisa,
out?
do you want me to take notes while folks are talking
Sure.
about
Yeah.
ideas? Okay.
Yeah. And I'm trying to do the same. So excuse me. So one of the things that I heard people talking about, and there's been a little bit of talk about it since, is an idea of a trail map. But then that idea started to fall apart because state parks didn't want you to make the trail map or something. Can someone talk about that project? I forget the name of that trail. Who was that working?
I can speak to that. This is Rini.
Rini,
So
okay.
this was for Fall Creek
Yes.
as part of the Henry Cowell. And we contacted state parks, and they said basically they have a pretty extensive approval process, and that we wouldn't be able to do it within the 8-week time period.
Okay. So where is that group thinking that they're shifting?
So we came up with a totally different idea.
Okay.
Sort of totally different. I don't know if you've heard of the soundscapes of Point Reyes or soundscapes of the seashore from Point Reyes State Park. It's really cool. I can share the link in a second, but it's kind of like they created sound recordings of various trails at Point Reyes, and then like combine that with like illustration and photographs, and it's a website now, and you can go in and like experience the trails of Point Reyes. So something like that, but like maybe different locations around Monterey. Like we could either all record one area and like do it together, or we could each record different areas. Because like some of us live in Santa Cruz area and some of us live down in Monterey. The only barrier is what do we record with in terms of quality. Phones are not great quality, and so I was wondering if you know of anywhere we could rent equipment, or if anybody has any like connections in that. It doesn't have to be super like fancy stuff like little pocket recorders. I'm probably gonna buy one for myself because I want to do nature recording anyways. So we would at least have one. But yeah, that's the general idea.
Okay. All right.
Does that
So
make sense?
all right. So, and was there more than you, Morgan, that is interested in this? Are there other folks?
Yeah. So it was me, Ben, Priscilla, and then Rini and Jill. I don't know if you guys were going to jump in on that or possibly do something different.
I think we're still thinking about it. We were also looking at doing the Bumblebee Atlas.
Cool. Oh, and the other part of it was like, so we do the sound recordings and then kind of each come up with like a little nature journaling, or like if you don't want to draw, you could do like photos of the area. And like and I have a lot of experience with building websites and stuff. So like we could make a really easy free website to just host it and put it all on there. It would not be hard.
So all of these details will come together in your
Yeah,
proposal.
sorry.
So I'm gonna let you and your team kind of think through the details, but you are leading to an important piece. So I want everyone to think about what's the deliverable. What are you creating that someone can use, and what's the audience? Who's going to use this thing? And be sure you get that audience kind of invited in real early in the process, because like you all, I steered you towards the state parks because I said, you know, ask these folks what they need. Well, I'm glad I did, because you found out that they didn't want you to do this or didn't need you to do this or whatever. So definitely for everyone with your projects, think about what are you making and who's going to use it, because we really want you to make stuff that gets used. So hold all of your ideas there, Morgan. Thank you.
And I have one question. So Morgan, you said you might be able to post the link. I found something that's an NPS link, so I'm not sure. I'm betting you'd run into the same problems if it's the National Park Service, but you're talking about a separate website. But you said there was some link or something. I'd love to share that with
Yeah.
folks.
So I was just kind of wanted to model it after that. I didn't want to do it like with any specific organization. And the reason is because especially with any kind of government organization, or I just put it in the chat.
Thank you.
Sounds good. Okay.
Or nonprofit, like things take a long time to get
Yep.
done.
So then that will be your group's task, though, is to think of what are we making, and then who's going to use it, and how do we, you know, package it for them to use.
Yeah.
All right. So let me move on, because I want to like get a picture here of what some of the other projects are. Anybody else got a crew together that they've got something cooking?
So,
yeah.
Hi.
Kathy, what's going on?
Yeah, so there were a few of us. I think Julia and I got somewhere. We're thinking more interpretation, communication about climate change impacts on the kelp forest. And I talked with you a little bit about how maybe a museum could use that. It would be typically aimed for kiddos ages grades 6 through 12, or maybe even kindergarten through 12, something like that. I think also maybe docent training programs or teen volunteer programs could use that as well. I think, I don't know, maybe aquariums, local places like that. And then to clarify, when we're considering our audience and who might be able to use it, are we supposed to be getting like a set like approval from an organization saying like, hey, I would love to use this? Because with Rini and Jill's idea, you know, sometimes the field maps that are provided by the Park Service, while they're very, very cool, they're not always user friendly, if that makes sense. Or that just might be a me issue, which is likely. But do you know what I mean? Like, I would appreciate a field map developed by just avid hikers or something like that. Do we need like something like explicit approval from an organization?
Well, we don't always need explicit approval, but we want to have a way of getting, if you made a trail map, we would want to have a way of getting that out to people using the trail. So how are you going to be able to do that if you don't have it like in a little trail map holder at the trailhead, you know? And how do you get it in the trail map holder at the trailhead? Well, you get the state park to say, sure, we want that in our trail map holder, you know? So you just have to kind of like think down the road, how is this going to get to the user? So I just want to make sure that it does. All right. So Julia, Asaria, and Kathy, and who else is part of your crew? Anybody else on that team?
I think there are a few people still deciding. I don't know.
Okay. All right. That's good. We'll have some opportunities for people to jump into talking about some of these things. So for you all, your thinking now has to be like, let's make this a project that is doable in the remaining 8 weeks. You know what I mean? Because like you've got teens and kids and preschoolers and docents, and like maybe pick an age group and then kind of narrow it. And so, but you can do that. You all can do that. What else is cooking? Who else has something going on?
Rini and Jill, did you say something about the Bumblebee Atlas?
Yeah, we were looking at it, I think last night, and signed up to do the training. And so we were looking at participating in that. And I guess my question is, like, is our deliverable the data we're collecting?
So I would say just participating in a community science project, while it's a great thing to do, just participating alone is not probably a project, but doing something with that data you collect, like making something informational that would be used at the museum or at the monarch sanctuary, or creating something that would be used by somebody, I guess, is what I think would be a good deliverable for that. Or it could be maybe making your own handy dandy little 1-page, here's what you can do to observe bumblebees or something, for people.
And just FYI, the feedback I've heard from a lot of people about Bumblebee Atlas is it's really worthy, but it's really challenging. And people have suggested that, more support like that, something that really helps people use it or really know how to go about doing it and why it's valuable would be something useful. Again, though, the Bumblebee Atlas folks might not. It might be more of, they might not want you to do that, but I have heard a lot of people talk about how challenging it is.
It's really challenging. I've been part of it for a couple of years, and it's really intimidating to catch the bumblebees. So I don't know, Rini and Jill, if you want to chat later, I'd be happy to share my experience.
Yeah, I participated in it last year. And while they're challenging and a little intimidating, I got myself some good gloves to do it with, and I didn't want to keep them on ice too long. However, this year they are actually changing some of the protocols to make it more user friendly. And the really interesting part of it is when you start looking at, for example, there's the Franklin bumblebee that's basically going extinct, and some of the plants in our areas that the bumblebees, they do know that the bumblebees, when they have them in areas where there are things like blackberries and some of the berry crops that you have in the Pajaro Valley, that they increase their yield when they have the native bumblebees compared to something like the European honeybee. So there's a lot of information that could be shared, either like at a natural history museum or in that type of project with the Bumblebee Atlas.
Yeah.
And it actually opens on the 18th, which is cool.
Yeah. So taking what you learn and creating some things like that, particularly as it relates to agriculture, I think is extremely interesting in this area. That's great. Picking up a couple of questions from people, Irene is asking about examples of projects. There's some really old examples of projects in our class webpage at the bottom. Kat can probably steer you towards or talk with you about some examples of projects as well. And Kathy asked about, is there a group size? I just ask that you do group projects in large part because it's just too hard for me to kind of like help, 25 different projects, but I can help 8 different projects. So I would say a group size of 2 is, or up to, maybe 4 or 5. If your group's getting bigger than that, then you need to probably splinter off and make a couple of smaller groups, or have the group focus on 2 different things that is related, and you can still all meet together, but needs to have maybe 2 kind of distinct deliverables or something. So that's just a guideline, but I'm super flexible on this. We did talk on Saturday with a group that was doing some kind of a weed documentation of a invasive plant kind of thing. Can someone speak to that about what that project's looking like? It was some San Jose folks, maybe? maybe they're not around.
Yeah.
I know the best to talk about this because I have a lot of background noise right now, but
Oh, okay.
Go ahead.
we were talking about some sort of habitat restoration project, either involving first documenting all the species in an area and or starting to remove the invasive species as we figure out what those are and how to do so. We were just talking about, options for different locations for this. A lot of people were interested in this because they had creeks in their own, near their own houses or actually on their property. And we had talked about land that is under city jurisdiction and also possibly for California state parks. So I'm a little fuzzy on what our deliverable might be. If it could be just a species list, does that need to be something the organization that manages the land can use, or does it need to be something the public can use? And then, or can our deliverable just be improved habitat in that after we physically remove invasive species in a plot?
Certainly, yeah, I think that would work fine as a deliverable. You'd need to, again, you got to work with an organization that's going to let you do that. So you got to kind of sort that out. So, who all is involved in that? Can you, Kristen?
I remember, I'm going through the list here. I remember, I think it was Dimitri, Chris, Rocco, Olivia. Let me know if I missed somebody.
Yeah, this is Ananta. I'm also interested in that.
And I think
Okay.
that was.
And am I right? You all are kind of San Jose focused folks. Is that right?
There's 2 people from San Jose and then 2 people from Monterey and somebody from Moss Landing and maybe Carmel Valley.
Okay. All right. Well, this gives me okay, this gives me a start. So what I'm going to do is I'm going to start to put together some folders, and I'm going to put in the summary for this week. I'm going to put links to different Google folders where you all can start to work on some of these documents and start to kind of think through these ideas. And then that is also a place where you can kind of communicate with each other. Now, some of you are thinking, oh, I don't know what I'm doing. Don't worry about it. We're still going to get a chance for you to, excuse me, for us to kind of meet together in some groups, but we want to start to steer you towards some things. So if you want to have a little chat with me, chat with Kat, whatever, or throw ideas to us in the email this week and we can respond to you with our thoughts, glad to do it. But this gives me something to start on for now. And then you all can kind of opt in to that Google, those Google folders once I create them. So you can kind of join a group.
Hey, Lisa, is Bruce going to be leading the field trip at Fort Ord?
Ideally, it's David Steyer, but neither Bruce nor David Steyer will respond to me. So if anybody is friends with David Steyer,
talk to those native people.
What's that? Or Bruce Delgado, you guys can rattle them for me. All right, let me quickly just say for next week, we are having Jordi Vasquez from the California Department of Water Resources will be talking with us. And he's got amazing information on California water resources and particularly the connection to climate change and a wealth of information. So you will look, please, by Friday, I will send you again a summary with lots of details with some supplementary readings and things, particularly a website to look at and some questions to ponder between now and next Wednesday. So no field trip on Saturday and chapter 3 water resources for next Wednesday. Any questions? All right. Thank you so much.
I'm saving the chat. So if anyone, I'll try to clean it up and share the links, especially the links that people posted.
All right, excellent. Thank you so much, and I will see you next week. Send us emails if you have any questions. Bye.
Thank you.